In many facilities, AC motor controllers are used to control and protect the operation of AC motors. When a controller malfunctions, you may be the person responsible for locating the cause of the problem and making the necessary corrections. In other words, you need to know how to troubleshoot. It's also important for you to know how to properly maintain controllers so that they operate with maximum efficiency and a minimum number of problems. In this part, we'll look at typical diagrams and charts that can be used to help maintain and troubleshoot AC motor controllers. Specifically, we'll look at examples of a schematic diagram and a wiring diagram. We'll also look at two types of charts, a legend and a sequencing chart. Schematic diagrams are diagrams that use letters, lines, and symbols to identify components and show how they're connected electrically. You can use a schematic of an AC motor controller to become familiar with the controller's components and how they operate. This is a schematic diagram of a typical AC motor controller. The controller has a motor or power circuit that provides power to the motor and a control circuit that can open or close the power circuit. A power source, which is not shown, is connected to line leads labeled L1, L2, and L3. The line leads are connected to three main contacts, which are each labeled with the letter M. These main contacts are normally open. The main contacts are connected to three overload devices, which are connected to three motor leads labeled T1, T2, and T3. The motor leads are connected to the motor. A step-down transformer is also connected to the power circuit. The transformer lowers or steps down the voltage used in the power circuit to a lower value that is used to operate the control circuit. The connections to the high side of the transformer are labeled H1 and H2, and the connections to the low side of the transformer are labeled X1 and X2. The transformer is connected to a pair of fuses labeled F1 and F2, which protect the motor controller from short circuits. If a short occurs, the fuses will blow, causing opens in the control circuit. The fuses are connected to stop and start buttons and to overload contacts. The overload contacts, which are labeled OL, are normally closed. The start button has maintaining contacts, labeled M. The maintaining contacts are auxiliary contacts operated by the M coil, which is also in the control circuit. All of the contacts labeled M are operated by the M coil. On this diagram, electrical connection points are indicated by numbers. The start button and the maintaining contacts are electrically connected to the control circuit at connection points 1 and 2, and the control circuit is connected to the X2 side of the transformer through fuse F2 at connection point 3. These numbers can be used as a reference when troubleshooting a controller, as we'll see later. Pushing the start button energizes the control circuit, including the M coil. When the M coil is energized, it closes all of the M contacts and power can flow to the motor. In this example, the start button is designed to be pushed in and released. After the start button has been released, the maintaining contacts, labeled M, remain closed to maintain current flow to the M coil. If an overload occurs, the overload devices open the overload contacts. Opening these contacts opens the control circuit, which stops current flow to the M coil. When the M coil is de-energized, the M contacts open. As a result, the path for current flow to the motor is interrupted and the motor stops. In order to stop the motor during normal operation, the stop button is pushed. Pushing the stop button opens the control circuit, which stops current flow to the M coil. The de-energized M coil opens the M contacts, interrupting the path for current flow to the motor, and the motor stops. Although a schematic diagram can help you become familiar with a controller's components and how they operate, it doesn't show you where the components are physically located in the controller. To see how the components are actually arranged, you need a wiring diagram. The wiring diagram is a graphic representation of the inside of the controller that shows the electrical connections and the approximate physical locations of the controller's components. You can use the wiring diagram as a guide to locate the components in the actual controller. For example, this wiring diagram represents the same components as the schematic diagram we looked at a moment ago. The motor or power circuit is represented by the heavy lines, and the control circuit is represented by the thin lines. The box on the wiring diagram represents the controller's physical enclosure. In this example, the fuses and the step-down transformer are located outside of the controller's physical enclosure, so they do not appear on the wiring diagram. The line leads and the motor leads are labeled the same way on the wiring diagram that they are on the schematic diagram. However, on the wiring diagram, the electrical connection points are indicated by circles instead of dots. For example, the H1 side of the transformer is connected to line lead L1 here, and the H2 side of the transformer is connected to line lead L2 here. There are actually 6 sets of main contacts in this controller, so the wiring diagram represents 6 sets of contacts. In the schematic, the 6 sets of contacts were represented by symbols for only 3 sets of contacts, because sets of contacts work in pairs. The overload devices are labeled OL and are numbered 1 through 3, as are the overload contacts. The stop and start buttons for the controller are not shown on this wiring diagram because these buttons are not physically located in the cabinet that houses the controller. However, the electrical connection points for the start switch and its maintaining contacts are indicated on the diagram by the points 1 and 2. These numbers correspond to the numbers on the schematic diagram, and they can be used as a reference during troubleshooting. As on the schematic, the M coil is represented on the wiring diagram by a circle with the letter M inside of it. One side of the M coil is connected to maintaining contacts and the start button at connection point 2. Although the maintaining contacts are in the control circuit, they are represented with heavy lines. This is because, like the main contacts, they are operated by the M coil. There are 2 sets of maintaining contacts in the controller, so the wiring diagram represents both sets. The other side of the M coil is connected to the 3 overload contacts. From the overload contacts, a wire connects the control circuit to connection point 3. Connection point 3 indicates where the control circuit is connected through fuse F2 to the X2 side of the transformer. Most motor controller diagrams are accompanied by 2 types of charts, legends and sequencing charts. Legends can help you identify the symbols and abbreviations used on the diagrams. For example, this legend shows that the letter M represents the controller's main contactor, and that OL1, OL2, and OL3 represent the overload devices for phases 1, 2, and 3, respectively. Sequencing charts show the positions of a controller's components during operation. There are many different types of sequencing charts, and they may indicate the positions of contacts or of relays and contactors. Contacts are usually shown on a sequencing chart as either open or closed, and relays and contactors are shown as either energized or de-energized. For example, this is a sequencing chart for a limit switch in a motor-operated valve. The chart shows 2 sets of contacts for the limit switch and indicates the position of the valve from fully closed to fully open. The darker portion of the solid bar indicates when the contacts are closed. When the valve is fully closed, contact set 2 is open, and at all other times, as indicated by the darker portion of the bar, contact set 2 is closed. Now, this is another type of sequencing chart for the same limit switch. This chart uses the letter X instead of a solid bar to indicate when contacts are closed. On this chart, contact positions are shown for 3 stages of operation: when the valve is fully closed, when the valve is in an intermediate position, that is, neither fully closed nor fully open, and when the valve is fully open. When you're troubleshooting an AC motor controller, Sequencing charts can be a valuable tool in determining how the controller is supposed to operate. They can also be helpful in determining the positions that switch contacts may be in during a malfunction, which may be a clue as to what went wrong. Take a moment now to check your understanding of diagrams and charts used with AC motor controllers by trying a question. In this part, we'll look at procedures that you can use when you have to locate the cause of an AC motor controller malfunction. In other words, when you're troubleshooting. A typical troubleshooting procedure can be broken down into a series of steps that you can follow. First, you need to know or understand how the controller normally operates. The second step is to question or investigate how the controller was actually operating during the malfunction. After you investigate, you need to evaluate or attempt to define the problem by comparing the controller's normal operation with how it's operating during the malfunction. The next step is to inspect the controller and examine its components. And then, after the cause has been identified, you should make the necessary repairs. Finally, after you've made the repairs, you should test the controller to make sure that it is operating correctly. Let's look at the steps in this procedure one at a time and see what can be involved. When you begin troubleshooting, it's important for you to fully understand how the controller should normally operate. If you don't know how the controller is supposed to operate, you can't effectively identify the symptoms of a problem and determine its possible causes. Many sources of information are available to help you determine how a controller normally operates. You may be familiar with the controller's operation from your own experience. If that's the case, you can draw on that experience to make troubleshooting less complicated. The person who operates the controller can be an excellent source of information as well. From working with the controller on a daily basis, that person should be quite familiar with its normal operation. Plant supervisors can be another good source. Many of them have worked their way up through the ranks, and they often know a lot about the normal operation of the facility's equipment. Schematic diagrams can help you identify the controller's components and how they are electrically connected. Using a schematic diagram to trace the current paths through the controller is one way to determine how the controller is supposed to work. Other sources of information include system description manuals and technical manuals. System description manuals typically describe what a system is, what components it contains, how the system and its components usually operate, and where each part of the system is located. And manufacturers sometimes supply technical manuals for their motor controllers. These manuals describe normal controller operation and provide other pertinent information. Once you know how the controller should operate, you can investigate how the controller is actually operating during the malfunction. To do this, you have to identify the symptoms of the problem and then decide what to do about them. The operator who reported the problem is often the best source of information about the problem's symptoms. This person can most likely give you a clear description of what's going on. If this person is not available, you might be able to talk to the supervisor who received the trouble report, or read the trouble report yourself. In some cases, you may need to test run the controller so that you can observe the malfunction firsthand. But test running a controller can sometimes further complicate the problem. For example, if one of the symptoms was the smell of burnt insulation or smoke, a test run could further damage the insulation or cause a fire in the controller, so the situation should be evaluated before a test run is made. And whenever you do make a test run, make sure that all applicable procedures are followed. After you've investigated, you need to evaluate. In other words, you need to compare how the controller operates normally with how it operates during the malfunction. One of the best ways to evaluate is to list all the possible causes of the problem and then systematically examine each possibility. This way, you can narrow down the possible causes or pinpoint the actual cause. The controller schematic diagram is generally used during the evaluation process. The schematic shows you what the components are, how they're supposed to operate, and how current flows through the controller. With the schematic, you can compare what is happening with what is supposed to happen. That way, you can eliminate any components that are working correctly. After the possible causes of the controller malfunction have been narrowed down, the components that have not been eliminated should be carefully inspected. You can use the motor controller's wiring diagram as a guide to locate each component. During an inspection, it's important to follow all applicable safety precautions. You can usually begin your inspection by using your senses of sight, touch, and smell to thoroughly examine the controller. You should look for anything out of the ordinary, such as dirt, burnt insulation, broken wires, or loose parts. An unusual smell may indicate burnt insulation, and a hot spot may indicate overheating. If the visual inspection does not result in finding the cause of the problem, the next step, generally, is to take electrical test measurements. 3 common faults you can test for are grounds, opens, and shorts. Test procedures for each of these problems are covered in some detail in this unit in the topic called troubleshooting. Once the cause of the controller problem has been identified, the next step is to make the necessary repairs. Repairing an AC motor controller often includes replacing components that are malfunctioning. When replacements are made, the new components must be the same size and rating as the original components. If the cause of the malfunction is defective or damaged contacts, you should replace both the movable and stationary contacts at the same time so that they will make good clean contact when they're closed. After the repairs are made, the last troubleshooting task is to test the controller to make sure that it is operating correctly. To test a controller, you should operate it through all of its different operating modes to make sure that everything is operating the way it should and that there are no other signs of problems. While you're testing, pay special attention to any replaced or repaired components to ensure that they are operating correctly. Also, while you're testing, you may need to make adjustments to the controller and reset devices that require resetting. For example, after a pressure switch or a float switch is repaired or replaced, you may need to set the operating levels for the switch. Sometimes, several malfunctions occur in a controller at the same time. After each malfunction is corrected, other problems that are present and undetected will make themselves known during the test run. The new symptoms can then be evaluated, inspected, repaired, and tested. Take a moment now to check your understanding of how a malfunction in an AC motor controller can be identified and solved. In this topic, we introduced some diagrams, charts, and procedures that you can use to maintain and troubleshoot AC motor controllers. Try some practice questions now that relate to this material. In this part, we'll look at how you can troubleshoot an energized AC motor controller. Basically, there's one major reason for troubleshooting an AC motor controller while it is energized. Shutting down a controller can sometimes interfere with the operation of other equipment in the facility. For example, when 2 separate control systems receive their power through the same power supply breaker, opening the power supply breaker de-energizes both control systems, and that could be a problem. In a case like this, an electrician may first attempt to locate the problem by testing the malfunctioning controller while it is energized. It's important to remember that you should test an energized controller only if the symptoms of the malfunction indicate that testing will not further complicate the controller's problem. For example, symptoms such as the smell of burnt insulation, sparks, smoke, or glowing wires are warning signals that you should not test the controller while it's energized. When you're working on an energized controller, you must follow all applicable safety rules, including the use of safety glasses and the properly rated leather-covered rubber safety gloves. The 3 electrical problems that can occur in a controller are grounds, shorts, and opens. However, an energized controller is not usually tested for grounds and shorts. Although one ground in a controller circuit is measurable, it has little or no effect. In fact, some controllers are intentionally grounded. When a short occurs, the controller's fuses or circuit breaker open and the controller is de-energized. For this reason, energized controllers are not normally tested for grounds and shorts, but they are tested for opens. One way to test an energized controller for opens is to test for voltage drops across various parts of the controller's circuits. Generally, If an open exists in a circuit, there will be a voltage drop in that part of the circuit. Let's follow an electrician as he uses a voltage tester to check for an open in an energized motor controller. In this example, the electrician has already evaluated the symptoms of a controller malfunction and has narrowed down the possible causes of the problem with the aid of a schematic diagram. He thinks that the problem is probably in the controller's maintaining contacts or in the wires leading to the maintaining contacts. This is a simplified schematic of the motor controller's control circuit. It includes the stop button, the start button and its maintaining contacts, and the M coil. This symbol, a circle with the letter V inside, represents the voltage tester. The lines connected to it represent the test probes. One test probe is placed at the electrical connection point on one side of the maintaining contacts, and the other probe is placed at the electrical connection point on the other side. The maintaining contacts are normally open, so current flows from line lead L1 through the circuit and the voltage tester to line lead L2. If the wires leading to the maintaining contacts are good, the voltage reading should indicate full line voltage, and it does. Since the wires leading to the maintaining contacts are good, the malfunction has to be caused by a problem with the maintaining contacts themselves. Now let's look at another example that's a little more involved. We'll use a simplified schematic of a controller's control circuit to see how you can troubleshoot an energized controller that has a malfunctioning stop button. This simplified diagram represents the controller's control circuit. The malfunctioning stop button is represented in the open position. The electrical connection points shown on the diagram are numbered from 1 through 8 for ease of reference. In this example, the only identifiable symptom of the controller malfunction is that the motor will not start. One way to isolate the cause of the malfunction is to take voltage readings across each component in the control circuit. The first step is to verify that power is available from line lead L1 to line lead L2. The electrician uses a voltage tester to make the test. The meter indicates full line voltage, which means that power is available. The next step is to place one of the probes on L1 and the other on electrical connection point 2. If the circuit from L2 through the M coil is complete, voltage will reach connection point 2, and the voltage tester will indicate full line voltage. When the electrician conducts the test, the voltage tester gives a full line voltage reading. Voltage is reaching connection point 2, so the M coil and the wiring from the M coil to L2 are good. The power supply, the M coil, and the wiring from the M coil to L2 can be eliminated as the cause of the problem. The next test is made from L1 to connection point 4, and the voltage tester again indicates full line voltage. This means that there is a complete voltage path from L2 to connection point 4, so the wiring and components from point 4 to L2 can also be eliminated as a cause of the problem. The next test is made from connection point 4 to connection point 8. Again, the reading is good, so the electrician knows that the wires from L1 to connection point 8 are okay. At this point, the wiring and components from connection point 4 to line lead L2 and from connection point 8 to line lead L1 can be eliminated as the cause of the problem. This means that the open must exist somewhere between connection point 8 and connection point 4. So the final test is made from connection point 7 on the other side of the stop button to connection point 4. The voltage tester reading for this test is 0, which means that voltage is unable to reach connection point 7. This reading indicates that the stop button is malfunctioning and is, in effect, open. The problem is now isolated and it can be corrected. In this part, we'll look at how to troubleshoot a de-energized controller to determine the cause of a malfunction. We'll see how to test the controller to make sure it is de-energized, and then we'll look at how you can test the controller for grounds, opens, and shorts. Generally speaking, there are two reasons for de-energizing a controller before troubleshooting: to prevent personal injury and to prevent further damage to the equipment. For example, if there is a short in a controller, leaving the controller energized could damage the controller further. In addition, megometers and multimeters, which are the test instruments typically used to test for grounds and shorts, can be damaged or destroyed if they're used on energized equipment. After the controller has been de-energized, locked, and tagged according to your company's procedures, it should be tested to make sure that it is de-energized. You can use a voltage tester to test all three phases, phase to phase and phase to ground. After you're sure that the controller is de-energized, you can proceed with testing. We'll begin by looking at how a de-energized controller can be tested for grounds. Although one ground in a controller circuit is measurable, it has little or no effect on the normal operation of the controller. However, if two grounds occur in the same circuit, the result is a short. When a short is caused by a ground, normal controller operation is affected. So when the symptoms of a short are present, it's often necessary to test the controller for grounds. Testing a controller for grounds involves taking resistance measurements to ground for the complete controller circuits. A high or infinite resistance reading indicates that a ground does not exist in the circuit, while a low resistance measurement indicates that a ground is present. Two test instruments that can be used to test for grounds are a high-range ohm meter, called a megometer, and a multimeter that is set for resistance measurements. The one we'll look at is the megometer. There are several types of megometers. Some are powered by a hand-cranked generator, and others are line-powered. The one used in our example is cranked by hand. Before using the megometer to test for grounds, the electrician tests the instrument to make sure that it's operating properly. To do this, he clips the meter's two probes together and then operates the meter. The meter should indicate zero resistance, and it does. Next, the electrician separates the probes and operates the megometer again. This time it indicates infinite resistance, as it should. Finally, the electrician connects both probes to ground and operates the meter. This time, the meter should indicate a zero reading, and it does. Once he's sure that the megometer is operating properly, the electrician can begin testing the de-energized controller. This simplified schematic represents the control circuit of an AC motor controller with a megometer, which is represented by a circle with the letter M and the Greek letter omega for ohms inside of it. One of the megometer's test leads has already been attached to ground on the controller cabinet, as indicated by this symbol, which represents ground. The other test lead is placed on the output of the fuse labeled A. With these connections, this portion of the circuit will be tested when the megometer is operated. In this case, the megometer indicates a high reading, so there is no ground here. To check the remaining portion of the circuit for grounds, the megometer test lead that's attached to ground is left in place, and the other test lead is moved from fuse A to fuse B. Again, the megometer's reading indicates a high reading, so there is no ground in this portion of the circuit either. In this example, these two tests for grounds are enough to cover the entire control circuit because the circuit is divided into two parts by the open start button and its open maintaining contacts. Another test that is commonly made on de-energized controllers is the test for opens. One way to test for opens is to use a multimeter set for resistance. Each component under consideration is tested by placing the multimeter test leads on the component's electrical connection points. When a component is tested for opens, the component's resistance is measured. The first step in using a multimeter to test for opens is to zero the multimeter. On this multimeter, the electrician selects the appropriate resistance range, then touches the multimeter probes together to zero the meter. Before a component is tested, the electrician disconnects one of the wires leading to that component to prevent a parallel current path. We can use a simplified schematic to see what can happen if this is not done. In this example, we'll be testing the M coil. This diagram shows the control circuit of an AC motor controller and a multimeter. The multimeter is represented by a circle containing the letters MULTI. One of the multimeter's probes is placed on the electrical connection point on one side of the M coil, and the other probe is placed on the connection point on the other side of the M coil. This symbol represents an indicating light. The indicating light is in a portion of the circuit that's in parallel with the portion containing the M coil. Unless one of the wires connecting the M-coil to the control circuit is disconnected, the multimeter will measure both the M-coil and the indicating light, so the reading would not be an accurate measurement of the M-coil's resistance. So one of the wires leading to the M-coil is disconnected. If an open does not exist in the M-coil, current flows from the multimeter through the M-coil and back through the multimeter. If there is an open in the M-coil, current cannot flow through the M-coil back to the multimeter, and the meter would indicate a high or infinite resistance. So far, we've looked at how a de-energized controller can be tested for grounds and opens. The last type of test we'll look at is the test for shorts. Testing a de-energized controller for shorts is exactly the same as testing the controller for opens, except that the expected results are different. An open results in a higher than normal resistance reading, or infinity, while the reading for a short is lower than normal. To test for shorts, the electrician takes a resistance reading for each component under consideration. For example, to test the M-coil, one of the wires leading to the M-coil is disconnected to prevent a parallel current path, and the multimeter's test probes are placed on either side of the M-coil. If a short exists in the M-coil, there will be a low resistance path through the M-coil. This means that current will flow from the multimeter along the low resistance path through the operating coil and back through the multimeter. In this case, the multimeter would indicate lower than normal resistance. In this part, we'll look at how you can clean an AC motor controller. Cleaning is an important part of preventive maintenance. There are several important reasons why an AC motor controller should be kept clean. For example, dust and dirt can obscure controller problems. In other words, dust and dirt covering a component can hide its condition. Dust, dirt, or other contamination inside a controller's circuitry can also cause shorts or grounds. And if dirt gets between contacts, it can prevent the contacts from closing properly, which can result in an incomplete circuit. Another reason for cleaning a controller's contacts is that contamination on contacts can cause an increase in resistance. Increased resistance, in turn, can result in the generation of excessive heat, which can damage contacts and burn insulation. Cleaning and other preventive maintenance tasks on an AC motor controller should be performed only after the controller has been de-energized and locked and tagged according to your company's procedures. Then remove the controller's cover and test the controller to make sure that it is de-energized. While you're cleaning the controller, wear safety goggles or other protective eyewear and be sure to follow all applicable company procedures. You can clean an AC motor controller by using a clean cloth, a soft brush, or a vacuum to remove dust, dirt, and other contamination. When you're cleaning a controller, work carefully and get the controller as clean as possible. In this part, we'll look at how you can inspect an AC motor controller's components to identify potential problems. Inspections are generally done after the controller has been de-energized, locked and tagged, and cleaned. This way, the controller will be safe to work on and contamination won't hide the condition of any of the controller's parts. When you inspect the controller's magnetic contactor, be sure to check it thoroughly for loose pins and screws and for broken parts. After you complete the visual inspection, remove the armature and movable contacts. Then clean both the stationary contacts and the movable contacts with a soft brush to remove dust and dirt. Then examine each movable contact and stationary contact to see if it is pitted or badly burned. Pitted or badly burned copper contacts can be filed or sanded until they are smooth and clean, or they can be replaced. The contact's original contour should be maintained when it is sanded or filed, or else the contact may not close properly when it is operated. When the original contour of a contact cannot be maintained, the contact should be replaced. You should also check the face of the contactor's armature and the iron core for rust and dirt. Any traces of rust or dirt should be removed with fine-grade sandpaper. Rust or dirt could prevent the armature and core from closing completely and cause the contactor to make a noise that's commonly referred to as a 60-cycle hum. In addition, If the armature cannot close completely, resistance will increase and heat will build up, possibly resulting in burned contacts. After the contacts and armature have been examined and any necessary repairs have been made, the movable contacts can be reinstalled and properly aligned. Once the contacts are in the proper position, the contactor's armature can be manipulated by hand to check for free movement and proper operation of the contacts. After you've examined the contactor and its parts, you should carefully examine all of the other controller components to make sure that they are in good operating condition. For example, check the fuse holder clips for tightness and make sure that the fuses are the proper size and in good condition. It's also important to check the insulation on the controller's wiring. Any damaged wiring should be replaced. Silver contacts should not be filed or sanded. Filing or sanding silver contacts could remove the silver plating and damage the effectiveness of the contacts. When silver contacts are pitted or badly burned, they should be replaced. When either silver contacts or copper contacts are replaced, both the movable contact and the stationary contact should be replaced to ensure proper seating in the contactor. You may notice that a black film has formed on the surfaces of the contacts. On copper contacts, this film is copper oxide, which is a poor conductor of electricity. You can remove copper oxide by filing or sanding. The black film on silver contacts is silver oxide. Unlike copper oxide, silver oxide is a good conductor of electricity, so it should not be removed from contact surfaces. Be sure to check all the connection points in the controller with a screwdriver to make sure that they are mechanically tight. If they aren't, tighten them. After you have thoroughly examined the controller and made any necessary repairs, you can energize the controller according to company procedures. Then, make a test run to make sure that the controller is operating correctly.